This is a short video update on my Nixie clock that I'm building. I've just got them lashed up on breadboards and bits and pieces at the moment. Top of the picture you can see temporary 160 volt supply for the neon. It'll be very much miniaturized for the final clock, but this gives me plenty of oomph for experimenting on multiple displays, and it'll just take a lot of punishment. Next to that you can see the Nixie driver board, which I'll come to in a moment. This is the main processor board, which is a Micromite system. You can see the Micromite chip there. I'll describe this in more detail when it's more or less populated now, but it'll have various real-time clock board and temperature, humidity sensors and so forth on it eventually. It's Mighty Micromite by Jeff Graham, a fantastic system. I'll go into it in more detail in another video, but suffice to say that all you need is the chip, which is a PIC32 series chip, and the yellow capacitor above it. That's it. Chip costs about 8 Aussie dollars, $6 US, programmed, and it comes with a full basic interpreter on the chip. The chip will hold about 2,500 lines of code, basic code, and it'll run about 30,000 lines a second. Sorry. So it's powerful enough for this sort of thing, I guess. But you can put blocks of C language in there if you want it to go faster, and it's just a fabulous system. And open source and free, fantastic. Anyway, that's the processor board. What I want to look at today is this is my seconds display board, the driver board for the seconds display, which will consist of 60 IN1 neons. Some of these I've realised I've connected up the wrong way, and because the anode and the cathode are different shapes, it needs to be connected up the right way, so you'll see variations in intensity and that on this board. Obviously be resolved for the final thing. So I wanted every neon to be individually addressable, and so what I've done is I've used 8 chips on 2 boards, and they're the PCF 8574 I2C to parallel converters. Each one has a 2-pin I2C input and 8 outputs. Those 8 pins can be outputs or inputs, which I'll come to in a minute, but they're just outputs on this design. And we've got 8 high voltage transistors and a resistor between, a base resistor on each one. And that's all she wrote, really. And so I haven't gone for multiplexing at all on this design. I want everything to be individually addressable, including the Nixie tubes, and that's what these chips will do for us. So all of these neons are just driven by 2 data, a clock and a data I2C input, and the chip looks like this. Oops. Okay. So this is the 8574. I think a very useful chip, actually. The I2C address is set by using the pins 1, 2 and 3 top left. Just connect them to plus 5 volts or ground, and the one I showed there gives an address of 010. They come in 2 variants, the 8574 and the 8574A, and the difference is, as you can see from the top, the address ranges are different. So those 3 pins give you a different address range on the 8574 compared with the 8574A. So obviously 3 pins give you 8 addresses, and using the 2 chip variants you get 16 addresses. So you can hang 16 of these chips off two data lines, and each chip has got 8 inputs or outputs. If you want to use them as inputs, then the chip can send an interrupt signal to your processor when any of them changes, so you don't have to keep monitoring them. And if you want to use them as outputs, as I am, then you just send the appropriate I2C command over the data lines, and they do their business. So fantastic. So for 2 leads or 2 pins on your processor, you can have hundreds of inputs and outputs by just chaining these or putting these on the I2C bus. Okay, so this is what the display looks like. This is how it'll look typically, counting seconds around the clock, which is pretty straightforward, and there's probably a few code bugs and so on need to be ironed out. Some people say, oh, interpreted language, basic chip, speed problems. I think you see from this though that there's not a speed problem really with the chip or with the I2C chips. I think it works at 100 kilohertz. So, and this is just a random, showing the addressable nature of every LED. The Micromite is just generating random sequences in this little display. And there's no doubt about it that for most of the stuff that you're likely to be doing at home, the chip has enough power. And the different sequences are really only limited by your imagination, I guess, and your programming skill. Okay, thank you.